conference to more folks around the world, which is good. But it definitely loses something also. So I have 2:30, so why don't we get started, and we don't want to impinge too much on Charles's time. So I'll introduce the next speaker. The next speaker will be Charles Stine from Brandeis, speaking on the complexity of shake slice knots.
Excellent. Thank you, Greg, for the introduction, and thank you to the organizers for inviting me to speak at this conference. So today I'd like to tell you all about the complexity of shake slice knots. Now, I imagine the word knot is very familiar to this audience, and perhaps shake slices too, but complexity in this setting may require some definition. So let's jump right in with some background and some motivation. So the background and the motivation here is the study of smooth, closed, simply connected, oriented four manifolds, which the classification of such objects is, of course, a wide open problem, which many of us probably don't think will be solved within our lifetimes. However, there are some very natural questions which one can ask about such a manifold, which are left over from the days of the heyday of surgery theory and the attempt to classify such spaces. And the particular questions we're going to be interested in today are based on the following. So consider two classes alpha and beta in the second homology group of such a four manifold. And by simple connectivity, such and the Hurewicz theorem, such alpha and beta can always be represented by immersed two spheres. Moreover, consider classes with the following intersection data. So the two homology classes have intersection number 1, alpha has intersection number arbitrary n, and beta has intersection number 0. In surgery theory, this is called a hyperbolic pair. And there's a natural set of questions you can ask when you see this in H2 of such a four manifold. The first is, are there embedded spheres S alpha and S beta in your four manifold which realize these classes? And the answer to this question in the topological category is yes. That's the Fields Medal winning result of Michael Friedman, which led ultimately to the classification, the topological classification of smooth, simply connected four manifolds. But if you're not working in the topological setting, you can ask, well, okay, on the off chance that such spheres exist, do their geometric intersection data equal their algebraic intersection data? So when we actually start looking at the number of intersection points and the signs of the intersection points of these spheres, do the sign counts of intersections match up with the, or do the absolute counts of intersections match up with the sign counts? And generically, this doesn't happen even when such spheres exist. And so that motivates the following sort of definition, which is the complexity of the pair alpha and beta. And so in the case where we can find such spheres, what we do is we look at the number of pairs of extra intersections. So we take the absolute number of intersections, we subtract off the homologically essential ones, we're left with an even number, which we can then divide by 2 to get the number of geometrically essential but algebraically canceling pairs. And we can sort of view this as the natural obstruction to running the surgery theoretic machinery on smooth, simply connected, closed-oriented four manifolds. So here's a sort of the motivating question of today's work, which is there any setting, even a very restricted setting, in which we can sort of get a handle on both of these questions? That is, we can get a positive answer to one, and we can get pretty complete information about question 2. And in particular, can we exhibit all possible values of this complexity? And so I'd like to propose such a setting. So I'm going to work with a very simple class of four manifolds today called knot traces. So these are four manifolds associated to a pair consisting of a knot in the 3-sphere and an integer n. The manifold X of nk, the knot trace, is obtained by taking the 4-ball and attaching an index 2 4-dimensional handle, which is parameterized here as d2 cross d2 with one disk called the core and the other the co-core. And we attach this handle by gluing the boundary of the core times the co-core to a neighborhood of k according to the framing data n. So some things to note about this family of manifolds. For any n and any k, these are all homotopy equivalent to two spheres. And you can see the homotopy equivalence by simply crushing the four-ball to the point, and then crushing each separate co-core factor to a point. And that gives you your deformation retraction onto a sphere. In this setting, we have some natural analogs of the homology classes I was mentioning earlier. If we take a ciphered surface for our knot K and cap it off with a copy of the core of the two handle, we get a closed surface which generates the homology of the trace, the second homology of the trace. And likewise, if we consider the relative class given by the co-core, that gives us a non-trivial relative class which has self-intersection 0. And in fact, this class is sort of represented by an obvious punctured sphere, which is given by the co-core itself. So a natural question to ask is, when can we find a better surface to represent alpha? So when can we, because ciphered surfaces for non-trivial knots are never just disks. So in order to have a positive answer to question 1, we need our knots to have, we need some condition on our knots. So the easiest condition to impose is to make our knots slice. In this case, we get a candidate for S alpha, which is given by a slice disk living in the four-ball and the core disk of the two handle. And clearly this sphere exists in any knot trace. It's sort of independent of N. But this isn't the only way we can have this condition. In fact, it was shown by Akbulut in 1977 that it's possible to have these spheres exist in these knot traces without the knots themselves being sliced. And so we call these knots N-shake slice knots, where N is the framing associated to the trace. And so long as we restrict to N-shake slice knots, we can now start to think about answering question 2. Which is about the complexity, the geometric intersection number between this sphere and the co-core of the two handle. So here is the definition of complexity from the previous slide, but this time phrased in the setting of knot traces. So what we're doing is we're taking an N-shake slice knot, we're looking at all spheres S alpha, which generate the second homology, and we're looking at the minimum of the number of geometric intersection points between the sphere and the co-core minus the single algebraically essential point, and then we cut that number by a half so that we're honestly counting pairs instead of individual points. Right, so intuitively this is counting the number of algebraically canceling pairs of intersection points between the surfaces, and as I said, measures the degree to which question 2 fails. So our main theorem today is that for any framing n not equal to 0, and for any target complexity C, there exists a knot K sub nc sitting in S3, which is smoothly n-shaped slice and has complexity at least C. And in fact, I didn't include these examples in my paper, though I probably should in a revised version. I can actually give examples where the lower bound is realized. Okay, so how are these knots constructed? So the knots K and C are very large satellite knots, which Colin kindly defined for me in his talk. And the lower bound comes from computing the Levene-Tristram signature of the knot. And you might ask why I didn't use a more modern invariant to try and do this. And there's a very good reason for that, which I hope to explain in a few moments. So let's talk a little bit about where exactly these knots come from. So I'll briefly review the construction of satellite knots. So the starting data we need for this is a knot K in the 3-sphere and an embedding of the circle into the solid torus, which we call a pattern. And then we essentially compose these two embeddings. We define the satellite knot P of K by looking at the composition of the pattern embedding with an identification I that we choose between the solid torus containing the pattern and the regular neighborhood of the knot K in S3. And of course, if we treat this new knot P of K as a companion, we see that we can iterate this construction. computing P of K, P of P of K, P cubed of K, etc., to give an infinite family of knots in S3. So with this concept of iterated satellite constructions, we can define the knots case of NC. You choose your framing N and you choose your target complexity. And then there are a pair of patterns Q slash and Q for which you can form this 2C-fold composition, which I claim has is N-shaped slice and has the appropriate complexity. Now, a warning, these knots are somewhat impractical to draw since the crossing number is approximately a fixed constant K0 plus N raised to the power C. And K0 is not small. So this is, these things you definitely have to work with the patterns if you want to think about them. So here is the pattern Q. As you can see, its crossing number is quite large. To see it as an embedding of a circle into a solid torus, simply remove a neighborhood of the red unknot that you see sitting here in S3. What you're left with is an embedding of S1 into the solid torus. Likewise, here's the pattern Q slash. Now you will notice in my formula there was no explicit dependence on the framing N. That's because the pattern Q slash depends on the framing N in the form of introducing N plus 2 right-handed twists, full twists, in the 3 strands that pass through the box indicated here. So this is where the dependency on N comes in. So why should these large compositions be N-shaped slice? Well, it comes from the fact that the patterns Q and Q slash were constructed to have a topological property called dualizability. This is something that's built into them from their definition. And what this does is it gives us a diffeomorphism between the trace, the N trace associated to the knot case of NC, and the N trace of this other knot, which is displayed here in this formula. Now, the thing to notice about the knot on the right-hand side of this diffeomorphism is that, in fact, it's of the form the mirror of a knot connects some the knot, which we know from studying concordance that such knots are always smoothly sliced. And so, in particular, the trace on the right-hand side of this diffeomorphism is N-shaped slice for this very trivial reason. It's the trace of a sliced knot. So it has this sphere, which I described a few slides ago, generating its 2 homology. And we can pull back that sphere using the diffeomorphism D to obtain a possibly more tangled-looking sphere, but which nevertheless generates the 2 homology of the N trace of the knot case of NC. This proves that case of NC is an N-shaped sliced knot. So now, of course, it makes sense to talk about the complexity, since we have our sphere and we have our core. So how do we bound the complexity? Well, it turns out there's sort of a nice topological argument you can give, which shows that either the smooth or the topological 4 genus of a knot provides a lower bound. And you'll notice that's a bound which is independent of the framing. So it's quite the framing of the associated trace. So this is quite a strong lower bound. And the argument is essentially just that if you have a minimal sphere S alpha, you can add tubes to it to eliminate pairs of intersections with the co-core 2 by 2. However, most of the well-known genus bounds, so many of the ones that come from Heggart-Fleur, many of the ones that come from other flavors of Fleur homology, essentially all of those that have been defined in the last 30 or so years using analytic techniques, all of these genus bounds fundamentally work by bounding the genus of a generating class of an associated knot trace. And since all of our knot traces have second homology generated by spheres, all of these invariants are going to vanish for the knots that we're interested in. So this is what makes this exercise perhaps sort of interesting. And so a large part of the research was in fact looking for an invariant which doesn't vanish for this technical reason, which one can use to get a decent bound on complexity. And it turns out that if you go all the way back to 1969, Levine and Tristam's signature function, which is an even integer associated to a knot and a parameter t, actually gives an appropriate and working bound. So I should probably review what that is. So this invariant is going to be defined in terms of the following data. So P will pick to be our favorite prime number. T will be a pth root of unity, so that's a complex number on the unit circle. K will be our knot. A will be a Seifert matrix for K, coming from any Seifert surface. And then combining A and T, we will obtain this matrix B, which by examination one can quickly see is a Hermitian matrix. And since B is Hermitian, it has real eigenvalues. And so we can take the signed count of the eigenvalues and talk about the signature of this matrix. So this is precisely what Tristan did. So he defined the signature of K and T as the signature of this associated Hermitian matrix B. And he proved in 1969 that this is in fact an invariant of the pair KT. And moreover, half of its absolute value provides a lower bound on the 4 genus. Now, this invariant has a very, very nice property with respect to dualizable patterns, which Q and Q slash, the two patterns we use to construct our knots, are in fact dualizable. The property is that it converts satellite composition of such patterns into addition and subtraction. And so this allows us to compute the invariant of our target knot K sub NC in terms of the invariance of the two patterns applied to the unknot. And so if you follow through this calculation, you'll notice the effect, the net effect is that the composition exponent C ends up out front of the absolute value sign. And the quantity which we're left to study is simply the difference in signatures of Q slash and Q both applied to the unknot. So in fact, this means it suffices to find a pth root of unity T for some prime P such that these two signatures are not equal. And of course, one should note that because Q slash depends on the framing N, we have to find a general solution to this problem which works for all of the framings covered by our theorem. On the other hand, one of the things we're able to rig up by our specific construction of the pattern Q is that for any root of unity T, the signature is in fact identically 0. And this is independent of N because of course Q is independent of N. Q slash is where the dependency on N kicks in. So in particular, this reduces the problem to finding a pth root of unity T such that the signature of Q slash applied to T is not equal to 0. Given such a value of T, or a formula to find such T given our framing N, we then plug that into the computation we did on the previous slide, and we get that the 4 genus of our knot K sub NC is greater than or equal to our target complexity C, and therefore our target complexity is achieved. So how are we going to find this value, magical value of T? So we're going to use another property of the signature function, which is due to both Jerry Levine and Tristram, which is that given R naught K, and considering this signature function as a function of T, the signature function is piecewise constant, changing only when T passes a root of the Alexander polynomial. Moreover, if the Alexander polynomial changes sign at a root, then it follows that the signature has to change as well. And so, in fact, what we're going to do is we're actually going to work with the Alexander polynomial of our pattern of our knot Q slash applied to the unknot. So since sigma of Q applied to the unknot is identically 0, right, we just need to find some T value at which the Alexander polynomial of Q slash changes sign. It will follow that on one side or the other of that critical T value, the signature of Q slash is not equal to 0. And then that will be our T value to complete our calculation. Fantastic. So after doing, frankly, an embarrassing amount of matrix algebra, we find this general formula for the Alexander polynomials of our knots Q slash applied to the unknot. So you will notice the dependence on n here in the two factors in front of the first and third terms. And in particular, notice that when we plug the number 1 into this polynomial, we get the number 1 out. So in fact, we can take advantage of the intermediate value theorem to exert the existence of our sought after value t naught if we can show that there's some other value t minus where the Alexander polynomial is less than 0. T minus, of course, having to live on the unit circle in the complex numbers. So here's an idea. What happens to this polynomial if we take t to be an n plus first root of unity? Well, it simplifies dramatically. The factor of 1 over t to the n plus 1 and the factor of t to the n plus 1 disappear, and with that disappears all of our dependence on n. Moreover, we can group up the terms so that what's left contains the simple sum of t plus 1 over t, which, since t we assumed is a value on the unit circle in the complex plane, that's equivalent to twice the real part of t. And of course, for n not equal to 0, it's extremely well known that there are absolute value of n plus first roots of unity with twice real part minus 1 less than or equal to 0. So in turn, that implies that there must be a value of t for each n at which the Alexander polynomial of q slash changes sign, which implies there must be another value of t at which the signature of q slash is non-zero, which we can plug into the computation from the page several slides ago and use to obtain our complexity bound q. Thank you very much for listening.
Okay, let's thank Charles. And does anybody have any questions? I actually have a very elementary question way back in the definition of complexity. If you could.
Mm-hmm.
So in talking, you were saying that complexity is somewhat a measure of the difference between the actual number of geometric intersections and the algebraic number of intersections.
That's correct.
Right. But the algebraic intersection number could be negative, right?
Certainly. So it's yes. So I guess strictly speaking, I should probably have an absolute value sign hiding in here somewhere.
So that was my question.
Yes. I think that's probably a good catch.
Okay.
Yes. So you may notice in this line, I have I sort of implicitly put the absolute value in when I put the plus 1 here on the far right hand side.
I think it was even in the earlier definition.
Yes, and I think that probably needs to go a little earlier. So, that's a keen-eyed observation.
So you can't make something arbitrarily complex by having more and more negative.
Yes,
gotcha.
That is correct.
Any other questions? Okay, well, if there's no other questions, let's
I'm sorry, I have one.
Yes, please.
Yeah.
Is there some obstruction for it not to be shake slice in some sense?
Yeah, so there are many obstructions. So, well, I guess sort of the quickest way to answer that question is to look at the list of invariants which all have to vanish. So if you look at any of these concordance invariants, so tau, nu plus, TV plus the rotation number for a Legendrian representative, basically anything that comes from sort of modern gauge theoretic concordance invariants, all of those are going to provide obstructions in many cases to a not being n-shaped slice. So I mean, part of the reason the patterns Q and Q slash are so complicated and so large is that you sort of have to work very hard to construct a knot that is n-shaped slice but not slice.
Okay, thanks.